Welcome back, everybody. Welcome back to the channel. So today we're going to be continuing our little mini series talking about how to build an executable. Today we're going to be talking about is the symbol table. This is going to be the next largest part of processing data in our executable. So let's just jump right into it. Today we need to start creating symbols. So we're going to need to create a ton of symbols that are going to represent various different things. So this is mostly going to be just a setup, and then I think we'll be okay. Yeah, hopefully we can get through everything. But first, what we're going to do is we're going to create a symbol.header file. And this header file is going to contain all of the basic info. If you guys remember from my previous video, this is going to be the shared info that every single symbol shares. So we're going to have an external int of invalid address, a class representing class object, and then the symbol class. In the symbol class, we're going to have our basic constructor that's going to initialize this symbol. We're going to have this init function, which just initializes all of our values, and our free, which frees up some of the strings that we have in here. Now, when it comes to symbols, we're going to hold various different things. We're going to need to track what the address of the symbol is, the GUID, the name of the symbol, the full name of the symbol, the owner who owns that symbol, the flag of that symbol, the access flags of the symbol, and the data type. So those are all the basic things that we're going to need. And then for the symbol.cpp, we're just going to create an invalid address of this unique value. This is a very specific value that I've made. It's a random value, doesn't mean anything. However, when you are building your compiler and your virtual machine, you want to come up with a synchronized value that's going to be both on either side so that if you process information incorrectly, you'll know that if you have an invalid address of this value or an address of that value, you did something wrong. So that's kind of what I did. So now next we have our param header file. This is going to represent a param for a function, and that's going to include the symbol header file. And we're going to create a class of param that's going to hold a symbol pointer of a U type and whether or not it's an array. Now, if you guys remember, this is where the magic comes in because from here it's going to implement the symbol class. So method, field, and classes will all implement the symbol class. So when you pass it as a pointer, we'll know specifically what type of symbol it is by inspecting the symbol type here, and then we can cast it to the appropriate object. So that's kind of how that works. It's pretty cool. So now that we have our parameter, we want to create our method.h symbol. Now, there's a ton of stuff in here. I don't really have to go through everything, but I'll just go through the stuff that we care about currently. So if any of you guys are wondering, here's my imports. Now, all of these imports you're not going to have because there is some code in here that we won't be going over. Those are the imports that I have. So I have a struct called line data. I have, let's see, an opcode instruction called cache, an opcode instruction. Yeah, we'll go over that later. But an opcode instruction is a unsigned int. We have a function pointer. This is just, you can create these pointers. We'll just use them when we get around to them. But basically, this is used for the JIT system. I believe this is used for my Sharp native bridge, and these as well, because I have certain functions to access and handshake with the DLL or SL file. So there's just various data in there. We don't need to worry about that for now. Just create this data structure of method. So method is going to have various different data. So we're going to need to track how many JIT labels that we have. So it's going to be a pointer of N32, and that's going to be the total amount of JIT labels in our programming language. So the way it's going to work is, as you know, when you have a programming language, you can jump around to different addresses based on a goto statement. So once we generate the native source code for our method, we're going to need to save all of those addresses of each starting point of every single subsequent instruction inside of this array so we can access it later. We also want to have a UN32 of a bytecode. So if you remember before, it takes 4 bytes to build 1 bytecode, and each bytecode is going to represent a unsigned int 32. So that's going to be the code that we're going to execute for our function. We also have the function type, the stack size, how many the stack size, which is self-explanatory, how many params we have, the U type, which is going to represent the return type of the actual function. So it could return a function, it could return a function pointer, or whatever. So that's what that is. We also want to keep track of the array U type, so whether or not the U type is an array. I actually don't think I use this anywhere. The source file, that's going to be the address to the source file that this function references. The cache size, so how many instructions do we have? The delegate address, that's used for delegates. More on that later. The stack pointer offset, frame pointer offset, the frame stack offset. This is used for calling the function. We'll go over that later. It's just basic offsets to basically keep track of where we are and so we don't screw up the stack. Whether or not this is a native function, meaning that if we want to call this function, we need to execute the DLL. A bridge function pointer, which is going to represent a reference or a pointer to the actual function that we're going to be needing to execute when we call this on a DLL. Any params that the function has, an array of those, a list of try-catch data, and a list of line data. We also need more stuff. So this stuff is for the JIT. I mean, you can read this comment here, but basically this is data for tracking whether or not we need to compile the function. We have a int 16 of branches. So the way that this works in a very quick and fast and easy explanation, my programming language has a limit of what I call branches inside of a function. A branch qualifies as multiple different things. A branch can be a jumping around inside of a function due to an if statement or a goto statement. Branches also qualify as calling the function. So if you call the function once, that is also called a branch. It's basically just executing code that's not like straight line where you're bouncing around inside the function or bouncing out and coming back into the function. So that's what that is. And I believe my IR limit is 25,000. Yeah. So if I execute 25,000 branches inside of any given function, so if I call it 25,000 times, or I run a for loop of 25,000 elements or greater, then I would qualify that, or both, I would qualify that as a JIT event. I also have an int8 of JIT attempts. I can only do attempting 3 times to JIT the method. Sometimes compiling a function might fail. There could be multiple reasons. We could have low memory or whatever. So I just have multiple attempts to allow us to try to compile it. I also have whether or not this is a JIT function, whether or not the function is compiling. That way we don't try to JIT compile the same function more than once. And also the function pointer, which is the actual reference address to the JIT function. Finally, we have our free function, which just frees up all of our data. As you can see here, we just free up some of these. We call symbol.free, which frees up the name. And then we call free on a couple of other objects as well. We also have an init function, which just initializes everything. I'm pretty sure you can know what that does, and it's pretty straightforward. After that, we want to set up our line data. That's going to contain the PC or the program counter start of our line and the line number. So if you guys remember, if we go up to the bin, we have, where is it in the syntax.odf, and there, if I just scroll down to a random function, we have address at 0 or program counter at 0, line is 107, program counter at 5, address 5 is line 115. So that's kind of how that works. So if I go back, yep, you want to set that up and have your basic constructor. And that's it. So that's all we have to do for method. So now let's go look at other data structures. So now if we go back up to the symbols, next we're going to need to create a field. A field is going to represent a field in the programming language. So here are my imports, if any of you were wondering. We also have a class of class object. So this field, just like method, is going to inherit the symbol class. By the way, please make sure to put it as public. That way you can access the fields by just using dot notation access. And you want to create your constructor and your init, just like we always do. You also want to create an equals, which is going to pass in a reference to a field, and you can assign all those various different values. Finally, for a field, we have our specific types of data that we need. So we have our U type, which is going to represent the type of the field, whether or not it's an array, and whether or not this field is a thread local. After that, we have, let's see, we have class object. So finally, we want to create a class object. Class object is going to have a little bit more stuff. So we want to create our class of class object. We also want to have a data structure of method. Here are also my imports. And there I have in my class object, again, public symbol. I have a simple constructor, which immediately sets the type to a class. And as you can see, I just set everything to its default values. I have my standard init, which also does the same thing. And then I have a equals, which basically allows me to assign a class to this object, and I just copy the values. Now, here are the additional fields that class has. So I have how many fields do we have? How many methods do we have? And as you notice, if you notice, like this is a pointer. Fields is going to be just a pointer. This is a pointer because we want to be able to access a reference to those methods. We don't want to constantly have to create a new method every time that we add a method to a class. So we want to just reference it. But as far as fields, each class is going to have its own unique object for fields. We also want to know what's the superclass, how many interfaces do we have? Again, pointer because we don't want to create a bunch of class objects. How many static fields do we have? How many instance fields? The total field count, the method count, and the interface count. Now, these two are split up for a reason. It's very important why we do this. Now, I know this is a bit early, but looking down the line, the way it's going to work is we're going to have what's called our instance fields first, and then we're going to have our static fields second. And literally what we're going to do on the compiler side is from the start of our class all the way down to its lowest hierarchy point, we're going to realign the addresses from instance to static, meaning that if you have a static field in your current class and then a class that you inherit also has a static field, those two fields are going to be realigned to the back of the list, and any instance fields are going to be realigned to the front of the list. That way, when we have our garbage collector, when we're actually allocating these objects, I have what's called a new object, and I pass in whether or not this is a static initialization. If it's a static initialization, I set the size as well as the base address of where we're going to be looking to create these objects to either instance fields, meaning that at the very end of instance fields, we want to start looking at the static fields if this is a static init, or 0 if we want to look at instance fields. So I just wanted to kind of mention that really quick because that is very important. And finally, we have a few functions. So we have our free function, which just frees up some of our data. We also have a get field function, which allows you to pass in a name of the field, and then we go through the total field count, and we just check to see if the field's name matches. We also have a field index, which gets the index of that actual field. Same thing, we just check to see if the name of the field matches and then return the index. We also want to check to see if the class is related. This is kind of similar to what we do on the compiler side. We check to see if the class is not equal to null. We check to see if the GUID is equal to the current class's GUID. Otherwise, if the class has owner, that's wrong. So I'm going to say super. So if the class has a superclass, then we check to see if that superclass is also related to this class. So those are all the basic functions. Now let's actually look at the executable. So what we want to do is, now that we're here, now that we've processed our header section, we need to check to see if the current buffer or the current position at where we are in the file is equal to S symbol. That's going to be 0x05. Now, the reason why I do this is called section validation. I just made that name up. Basically, what it means is we want to validate that we are in fact in the correct section of code that we're supposed to be in the executable at the time of processing. Because if we're not, obviously, then anything that we're going to process after this is going to be incorrect and potentially dangerous to process. So we don't want to do that. So we just want to make sure that we're processing things correctly. We set up a few local variables here for different tracking. And then finally, we have, so now here's where it comes to actually assigning all of our data. So we have various different things here. Let's go through all the fields in my virtual machine. So in my virtual machine, and of course at the constructor level, I just set them to their default values. But I have all of these various different classes. We've gone over this before. These are frequently used classes. We have various different exceptions, and then I also have other mostly used classes like string class, stack state, the thread class, and the exception class. So various different classes I use. Now let's look at these. So I have a object of out of memory exception. We'll get into what an object is probably in a later episode, but there's that. I also have meta, which is going to hold the metadata, which consists of a list of source files, which contains other data inside of that object. We also have a manifest. Now you don't have to create this meta class yet. We'll go over that in a later episode when we get to the meta section. We also have a static heap. And as you notice, here's where it's important. This is a pointer of objects, and they're each a static heap. And if you remember, objects are merely containers for a sharp object. So as you can see down here, if I assign a sharp object to a new value, we decrement the reference of the current object that we have, and then we increment the reference of the new object that we have. So that's kind of how it works. So we have that. We also have a class array of any classes we have, a string array of any strings, a double array of any constants. We also have a method array of all of our methods, a symbol array of any native symbols, and a method array of function pointer symbols. We also have some GUID stuff. We're probably not going to go over that, so honestly, you can just leave that out. After that, we have a list of libraries, which a library, we can just create this now. A library is going to represent the actual data structure for SO libraries or any other type of library that we have in our programming language. This is basically going to represent our libraries, so a DLL file or an SO file. It's a very simple data structure. We just have a class of library, has a basic constructor, a basic init function, and we have two handles for each individual operating system. So for Windows, because I'm doing this on a Windows computer, it's called H instance, and I set a handle here, and then I have a void pointer of handle for the Linux operating system. And then I also have a native string of name, which is just going to be the name of the library. Now, where this data is inherited from is inherited from the string class, which also inherits the std imports, which then subsequently inherits. For POSIX, it is called dlfcn.h. That's how you include data to process DLLs. For Windows, I think you need windows.h. I'm pretty sure that's what it is, but you can check out all my various different includes here. So I have all these basic includes. I have the Windows include and others as well. So it's going to be one of these, but like I said, it's most likely just windows.h. Now let's go back to our executable so we can finish this up. So what we need to do is we need to use our manifest file to appropriately create all of these various different things. We need to assign our vm.classes equal to an array of classes using the malloc function, and we say size of class object times vm.manifest.classes. We do the same thing for methods. We use the data in the manifest to create how many methods we have. We also do this for the strings, for constants, for the static heap, same thing. Now for static heap, we need to assign, and I use calloc here because I want to initially set the sharp objects to null. So I use calloc, but we basically want to create the static heap the same size as how many total classes we have, because that's what the static heap is going to represent. We also have our metadata. We want to initialize our metadata. We want to set up our native symbols by passing in the native symbol count. That's going to be 14. What this does is this is basically a way for us to assign and create various different data in our virtual machine. So when we have symbols, we're going to have various different symbols that are going to represent different types. We're going to have symbols that represent int8, int16, 32, 64, all this stuff. So those are going to be the symbols that we create. We're also going to have var, object, and nil, I believe, which are going to all represent various different symbols in our programming language. So in an effort to save memory, whenever a function references a utype of nil, I'm going to use one of the symbols, or var. I'm going to use one of the symbols from the symbol list instead of creating a symbol every time. I used to create a symbol every time, and it was very memory consuming, so That's what I do there. I also set function pointers equal to a I32 of whatever it is inside the buffer, and then I malloc the function pointer symbols to the manifest function pointers. So once we do all of that, then we want to set up our native symbol count by initializing our symbol by setting all the default values and then simply just setting type to the data type at I. So we're going to go for 14. So basically we're going to, whoops, let me go back. Basically, we're going to go all the way up to 13 because it's 0 based, so we're going to go up to 14. So we're going to go from 0 to 13, and if we have any of these data types in here as native symbols, we can access them later. So now what we need to do is check to see if we have any of these values that are null. If any of these values are null, whether we have classes, methods, static heap, strings, I also need to add here or vm.constants. If any of these values are null, so equal to null, then we want to error out because obviously that means that we have a memory error. So we say fail to allocate memory for program out of memory. Finally, now we're down to here. Now, in an effort to keep this video short, I'm only going to process what's called a data symbol, and we'll get into processing data classes in the next episode. But basically, now that we have everything set up, we want to now process our first symbol. So what we're going to do is we're going to process our first symbol by assigning our current flag equal to the buffer at current position. So we're going to increment the position, check to see if the current flag, now if it's equal to 0, 0xa, or D, then we break. Those are characters that we don't care about. It's the same thing like we did up here in the manifest. We don't care about those characters, so we ignore them. So then we have a case where we have our data symbol, and in there, and you have to use these because if you're creating variables inside of a case statement, you have to use these brackets here to create your own scope. But we basically do a safety check to see if the function pointers processed is equal or greater than or equal to the function pointers. So what this basically is going to be is this data symbol is going to represent a function pointer. I don't know why I don't just call it data function pointer, but whatever. So we're going to basically create a method by getting a reference to the method at function pointer symbols, function pointers processed plus plus. The idea is that when we build our symbol table is going to consist of all of our function pointers. I completely messed up that word, but you guys get the point. So we have all of our function pointers, and then we have all of our classes. And that's how the compiler is going to generate this. And it's going to generate all of our function pointers from 0 all the way up to the number or the maximum amount of function pointers that we have. That way, if a function returns a function pointer or we have a field that is of type function pointer, we can reference this function pointer in an effort to save memory so we don't have to create those data types every time. In here, like I said, I access the current method and I initialize that method. I set the type equal to a function pointer or the function type. And then after that, I get how many parameters we have. So I get an I32 of parameters. And I say if param size is greater than 0, then I basically process the parameters by saying method.params is equal to a param array of param size. And in there, I for loop to the param size, and I assign the method params at I and the type of that parameter, and I set that equal to what I call get symbol. Now, this is a neat way for me to process symbols in my programming language. So basically what I do is whenever I need to process a symbol, what I do is I get an I32 from the buffer of a data type, and I check that data type to see what I need to do. So if the data type is equal to int8, if it's greater than or equal to int8 and less than or equal to int64, or it's of type var, or it's of type object, or it's of type nil, I return that native symbols that we were talking about. And it's going to be a reference to that. So these are all going to be pointers to those values. That way we can just access them as a reference. If it's a class, I get a reference from what the classes list is. Otherwise, if it's a function pointer, I get an access reference to the function pointer symbols. That way, if a function pointer returns a function pointer and I haven't processed that function pointer yet, it doesn't matter because all I'm doing is just getting the address of that function pointer. The fact that this function pointer hasn't been accessed yet doesn't matter. So this is where it kind of gets into how it can be easily dangerous to break the virtual machine, because if we're not processing data in our executable correctly, we could crash our virtual machine by accessing data that we shouldn't be accessing. So if I go back, so once we have gotten the symbol, then we want to get the params at I and set whether or not it's an array based on whether the current token is equal to 1. And then finally, we check to see if the param's utype is equal to null. I return a corrupt file. Because down here, as you can see, so if it's neither of these types, I set my exe error message to invalid field type found in symbol table. And this shouldn't be field type, it should just be type. Invalid type found in symbol table, and I return null. So once I do that, I basically return a corrupt file if the utype is equal to null. And then once I get out of this function, I print out that error message so the user knows what happens. So now that we've processed our parameters, now it's time for us to actually process the function. So we set the return type of the function to another symbol. We assign whether or not the function returns an array based on whether or not the next token is equal to 1. And then we check to see if the utype of that method is also equal to null. If it is, return a corrupt file. Finally, we break, and that's it. So that's going to be everything for today. We've kind of gotten our virtual machine set up. We've gotten all of our basic objects set up. So now we can just kind of go into how to process a class next. Shouldn't be too bad. And then finally, after that, we have, our string section, our constant section, and then our data section, which is a little bit hefty. And then, of course, our metadata section. So we still got a little bit more to go through. So we're going to keep pushing along. And yeah, hope you guys enjoyed the video. As usual, if you have any questions, as always, put them in the comment section below. And of course, if you would love to help support the channel, you can always head over to the GitHub repository at androidfcd/sharp. When you do, definitely watch, star, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you're curious about what I do on a daily basis, you can head over to the remastered branch, and there I write some pretty decent commits, so you can kind of get a gist of what I've been up to without really having to look too much in the code. Also, kind of like I mentioned before, I've done I think I'm on the 4th pass of this system. I still haven't committed the code yet, but it's now officially working with both Windows and Linux. I'm pretty proud about that, so if you want to check out that code, you can. Also, if you're curious about some of the things that I've done in the past or stuff that I'm looking to add in the future, you can always head over to the doc folder. And there's two main files. There's a changeless file. That's all the old stuff that I've done to the language. And the roadmap file contains all that information as well as new stuff that I'm looking to add in the future. So hope you guys enjoyed the video. As usual, if you're new to the channel, definitely consider subscribing. And until next time, see you guys later.